Welcome viewers to Bodhi Unified Flow. Here we simplify complexity and amplify performance. Today, we're unpacking a truly essential topic, Wallace, Hopp, and Mark Spearman's Factory Physics, Part 2, Little's Law and Basic Factory Dynamics. You know, if you've ever stood on a manufacturing floor and just wondered what invisible forces are really controlling the flow of materials, well, you're in exactly the right place. We're going to map out the fundamental, inescapable mathematical relationships that dictate how a factory actually behaves in the real world. So let's dive right in. Okay, here is our agenda for today's explainer. 1. Introduction and objectives. 2. Basic factory parameters. 3. Little's Law explained. 4. Best and worst case scenarios. 5. Practical worst case. And finally, 6. Variability and summary. Section 1. Introduction and objectives. Demystifying factory performance. Let's look at what we're aiming to achieve here. By the end of this session, you're going to have a rock-solid understanding of Little's Law and exactly how it relates your inventory to time and output. You'll be able to model the absolute best and worst-case scenarios, which sets the theoretical boundaries for your production lines. We're also going to apply practical worst-case formulas, giving you a realistic baseline for a less-than-perfect floor. And absolutely crucially, we'll see how variability essentially forces you to manage what Hopp and Spearman call buffers. Put simply, you'll walk away ready to confidently apply these principles to boost your throughput, manage your work in process, and slash those cycle times. Moving to Section 2, Basic Factory Parameters, the language of factory physics. Before we can do the math, we really need to agree on the vocabulary. First up is WIP, or work in process. Now, according to our source material, WIP is the physical inventory currently being worked on within your production line. It's the stuff actively moving between the start and end points of a routing. So we're talking about the product that's actually in the transformation phase. We are not talking about raw materials gathering dust in a warehouse, and we definitely aren't talking about finished goods waiting on a loading dock. Next, we have throughput, or TH. This measures the rate at which your system successfully pumps out output. And there's a really interesting distinction to make here. At the corporate level, throughput is usually defined as production that is sold. But let's be real, managers on the floor generally control what is made, not what the sales team actually sells. So for our purposes today, throughput is the average output per unit time. Think parts per hour or dollars of completed goods per day. Then there's cycle time, or CT. Simply put, this is the total average time it takes a specific job to travel from the very start of its routing all the way across the finish line. You might hear it called flow time or throughput time. Basically, it's the total delay your product experiences from start to finish. All right, so with those basics down, we need to define the physical limits of the line itself. First is the bottleneck rate, or RB. This is the rate of the workstation with the highest utilization. It's the absolute ceiling, the capacity limit of your entire line. Next is raw process time, or T0. This is the sum of the mean effective process times of all stations. Imagine dropping one single job into a totally empty factory where it never has to wait. That time is your T0. And finally, critical WIP, or W0. You get this by multiplying the bottleneck rate by the raw process time. Critical WIP is a magic number. It's the exact WIP level a perfectly balanced line with zero variability needs to hit maximum throughput with minimum cycle time. It's the ultimate ideal state. Section 3, Little's Law explained. The F equals MA of factory physics. Let's tie all these variables together with the big one. Little's Law. It simply states that work in process equals throughput multiplied by cycle time. Named after John D.C. Little, it is the inescapable core equation of factory dynamics. Think of it this way. These three variables are permanently locked together. You can't cheat the math. If you want to drop your cycle time but keep your throughput high, you have absolutely no choice but to reduce your WIP. And this holds true whether you're looking at a single workstation, an entire assembly line, or a massive global plant. You can even do the math in dollars. It is a fundamental, unbreakable law of manufacturing. Section 4. Best and worst case, the mathematical boundaries. Let's see what happens when we push this law to its absolute theoretical limits. Imagine the best case scenario, zero variability. Everything is perfect. You hit maximum throughput with the lowest possible cycle time. If your WIP is at or below that critical WIP we mentioned, your cycle time is just the raw process time. Nothing waits. It's beautiful. But now, look at the worst case scenario. In this nightmare, cycle time equals your WIP level multiplied by T0. Why? Because every single job is moving in one massive batch Everything waits for everything else at every single station. Throughput totally tanks. And here's the kicker. The authors note that both of these extremes happen in systems with no randomness. The worst case is terrible, yes, but it's entirely predictable because of terrible batching. It just goes to show that awful performance isn't always bad luck. Sometimes it's just bad control. Section 5. Practical worst case, reality on the factory floor. Because as we all know, real factories don't live in a world of theoretical extremes. Welcome to the messy middle, the practical worst case, or PWC. The best case is an impossible dream, and the worst case requires someone to intentionally mismanage the floor. So the practical worst case gives us a highly useful, realistic mathematical baseline. It models a line that is perfectly balanced but suffers from maximum practical randomness, highly variable process times. It acts as your ultimate benchmark. If your actual factory floor is performing worse in the PWC, you know for sure that your system has some serious, correctable flaws. So, how do we actually calculate this? In the practical worst case, your expected cycle time is your raw process time plus a weighting factor. That weighting factor is just your WIP level minus 1 divided by your bottleneck rate. On the flip side, the PWC throughput is your WIP level multiplied by the bottleneck rate, all divided by the critical WIP plus your WIP level minus 1. I know, reading math out loud can be a lot, but here is the massive takeaway. These formulas let you calculate the exact expected cycle time and throughput for whatever WIP you currently have. Plot these numbers, compare your actual daily performance against this curve, and you will see exactly how much everyday randomness is stealing from your bottom line. Section 6, Variability and Summary, the Corrupting Influence. So what's actually dragging us down from that perfect best-case scenario? The authors call it the law of variability. It is blunt, and it is absolute. Increasing variability always degrades the performance of a production system. Always. Maybe it's process variability, like unpredictable machine breakdowns or setup times. Or maybe it's flow variability, like late supplier deliveries or erratic batch sizes. Whatever the source, any chaos or lack of synchronization will inevitably damage your performance. It's an invisible tax on your whole system. And because it's a tax, somebody has to pay it. This leads directly to the law of variability buffering. Variability in any production system will always be buffered by some combination of three things: inventory, capacity, or time. Pick your poison. If your machines break down, you might hold excess inventory, extra WIP, just to keep the bottleneck fed. Or maybe you throw capacity at the problem, paying for overtime or buying redundant machines. And if you don't buffer with inventory or capacity, well, you're going to pay with time. Your cycle times will stretch, delays will pile up, and your customers will get very, very impatient. In fact, a truly lean system is simply one that minimizes the cost of these three buffers. All right, let's quickly summarize what we've achieved in this explainer. We proved that Little's law governs all production flow. We mapped out the absolute mathematical boundaries using the best and worst case scenarios. We brought it back to reality with a practical worst case model. And we exposed exactly how variability forces you to pay out of pocket for inventory, capacity, or time buffers. I'll leave you with this one provocative question to take back to your own operations. If you aren't actively, systematically reducing variability on your floor, which of those three expensive buffers, inventory, capacity, or time, is secretly eating into your profits right this second? Because according to the laws of factory physics, there is no escape. You are definitely paying for it somewhere. Thank you so much for joining this Bodhi Unified Flow Explainer. Every principle, law, and formula we broke down today is derived directly from the essential text, Factory Physics, 3rd edition by Wallace J. Hopp and Mark L. Spearman. Keep simplifying complexity, keep amplifying your performance, and we'll see you next time.